Welcome to BKW Physics. I'm Mr. McConnelly, and today we're going to study motion in terms of a graph, and we're going to study it through these three different toy vehicles that I have. I like to play with toys still, and I'm over 40 years old. Now the first one, that's a joke. The first one, I have this little Jeep here, but I do like to play with toys. In this Jeep, there's one of the ones you turn on, you turn the switch on, it just runs like this. And it just continues at that speed. It doesn't go faster or slower. This is one of those vehicles you pull back. Maybe it needs a tune-up or something. Let's try again. There we go. And then it kind of speeds up. And then this tow truck, it has nothing fancy. I'm just going to push the tow truck. By the way, this is the big pumpkin tow truck. No job is too large or too small for this. You can actually go down, back up.
You need to do that.
Oh. No hands. I pulled that in. That was nice, huh? So, but I don't really care that much. And so let's go through each of the motions of each of these vehicles. And I want you to specifically watch and think of what that would look like in a distance time graph. As you guys in the room have tried before, you had to move your body in such a way to match a graph. You did that as an activity. So we're going to look at this in terms of how these vehicles are moving distance time, and then how these vehicles are moving velocity time. So I want you to think of those two things as you watch this. First vehicle, the big pumpkin. My motion is going to go from this line to this line basically, maybe a little more, a little less, depending how I push it. Watch the motion. Okay? So again, I did that one better. Perfect distance. Okay, so that's the first one. And this is the Jeep vehicle. Kind of boring. Don't need to see that one twice. And then the sudden impact, which seems to have lost its impact over the years because the spring seems like it's kind of getting shot or something. It doesn't really go the way it used to. But I guess it's working. All right. Want to see that one more time? That one's pretty fun. I'm hoping it gets better too. Try again. Just sounds like something's slipping in there. Transmission's getting loose. All right, there you go. So we got, just for purposes of when we spin back to the board, we called this one the pullback vehicle, the sudden impact, the pullback vehicle, the Jeep, and the tow truck. So we can spin our attention to the boards for a second. You can just hold the base and boost that thing up. Kind of moves hard. If you keep it too low, then everyone's head blocks the view. So the Jeep. Let's look at the Jeep. If you were making a graph of the Jeep, distance time graph, and this was the starting point here, so you say the first line on the table, what would the distance time graph look like for the Jeep? Raise your hand if you know what I'm talking about here. Yeah. Straight diagonal line, I agree. Because after 1 second, it went this far. After 2 seconds, it went twice as far. After 3 seconds, it went 3 times as far. It was predictable. It just kept going at a predictable done. But in comparison, the tow truck did something very, very different. The tow truck was going along at a pretty good clip, and then the tow truck slowed down and actually came to a stop. How do you show that? Go ahead. It's going to have to level off out here. Agreed. How are we starting it though?
Same as diagonal, but then you move it to...
Alright, so we start coming up and then we kind of just flatten out until it flatlines. So that shows that in the beginning you're covering distance pretty quick. Pretty quick, slower, slower, slower. Oh, not covering any distance now. And if time continued, it would just stay there because it's just sitting there. Okay. And then the last one is the pullback vehicle. Pullback vehicle, when it worked, we pulled it back, we let go, and how'd the motion go on that one? So that one was speeding up, so it's kind of like taking this and just rearranging it a little bit because you end up ramping up. Maybe that's exaggerated. It really didn't go that fast. But it was ramping up. Sort of like that. Alright. Before I move on to the bottom set of graphs, I want to spend just a little bit more time reminding you of a few things that you probably remember, but I just want to make sure, is if you need to take the slope of this, how do you do so? Well, you pick a point here, you pick a point here, and you drop down, and this will tell you how much you changed your x variable, which in this case is time. And then you swing over this way, and you swing over this way, and that'll tell you how much you changed your y variable. So if you're doing the slope, it's the change in the x variable. No, that's not. I lied. It's the change in the y variable. It's always got to be y, so it's got to be. Change in the y variable over the change in the x variable. And when you divide those together, it'll tell you the slope. Now I want to stop here for a second and go a little more detail because the slope of this graph is actually something very useful. What's on the y-axis? Distance. I don't care about the numbers so much right now. What's on the x-axis? What is distance divided by time? Velocity. Oh my. So the slope of a distance-time graph will actually give me the velocity. In math class, you calculus types, there's a couple of you, you're gonna use this at a whole other level of math with integrals and derivatives, and you're going to be able to move between one graph and the other, and all of a sudden physics is going to start looking a lot like math class, and they're going to start overlapping in some cases. I love it. Alright, so that was the slope thing. Just a little side note there. Can you take the slope of a curved graph? Well, you could, but then you'd be like straightening out the slope, you know what I mean? You'd be like drawing a straight line through this, so it wouldn't really tell you much. But what you can do, if you need to, is if you, for instance, wanted to know something like, what's the velocity right there? That would be called instantaneous velocity. An instantaneous velocity means I don't really know anything else. I don't know what's going on either side of this, but I can find out information right there. It's like a freeze frame, like a picture. And so all I would do is if I took the distance right there and the time right there, again, distance divided by time is velocity. So it would tell me the velocity, but notice I didn't put a little average velocity because it's not. It's just the velocity at that point. See the difference? So that's instantaneous velocity. What does it tell me, these graphs, when they start down here?
That's the origin.
That's the origin. That's the starting point. Does that mean it had to be starting from a distance of 0?
Yeah.
No. In fact, the scale on these could be like 30, 20, 10, 0 could be way down here someplace. And in that case, I didn't start at 0. Okay? So you don't have to be starting at 0. Most people forget about that. Alright, let's move on to the velocity graphs. So with a velocity graph, let's think what was going on here. Let's start with that Jeep again. And that Jeep, what was the speed, the velocity? What was it doing? Staying the same. How do you draw that? So let's say the speed was, whatever this is, 5. Just stays at that speed. And that makes sense with what I've just told you up here, because if you took the slope way up here at the top, what would you get? Say the number was 5. What would you get the slope here? 5. What would you get the slope down here? 5. It's always the same slope because it's a straight line, so you were always going the same speed. That's why these two are the same, saying the same thing from a different perspective. Alright, go to the tow truck though. Tow truck's trickier. What's going to happen to that tow truck when you think about the speed on that? Is it a straight? Is it straight? Yeah, it's which probably gives you a big clue as to what's going on with the pullback toy. It's also straight, going upward. Okay, but that brings us to the next really important key concept here. The distance was curved. And in each case, a curved distance led to a straight linear velocity graph. Okay. Well, can we take the slope of these? Sure we can. So if you're taking the slope, you're doing the change in y over the change in x. The y variable in this case is, everyone? And the x variable is? Well, you don't know what that means yet. But I'm about ready to tell you. Velocity over time is acceleration. We'll come back to that more, speak about that more in the next few days. But what does acceleration generally mean? Acceleration generally means you're either speeding up or slowing down. Was this either speeding up or slowing down? Yes, in both cases you're either speeding up or slowing down. That's why we have acceleration, and that's why we can take the slope and get an acceleration. Okay? One last thing I want to do. There's also information that can be gained from any of these three graphs, which would, because so far we're going like, if you think about it, take the slope, it gives you this one. We'll wonder if we can do something and go back this way. Can we go in reverse? And that's the derivative integral thing I was talking about with math. But we can also do it in a more basic way here in physics class. If I were to, say, take the area of this part right here, how do you get area? You just do length times width, triangle shape, 1/2 base times height, right? But you basically, you times the two sides. So if you're doing area and you're timesing the two sides, like length times width, what's the length time? What's the length, the width side, whatever? Velocity. What is velocity times time? Distance. Ooh, this is awesome. So if I have one of these graphs, a distance time graph, I can get velocity. If I have a velocity graph, I can take the area and go backwards and get the distance. So I can go either way on these, making this a really handy feature here. Okay? And you can still do it with the triangles, it's just, you know, you got to do 1/2 velocity times time, but it's still going to give you the distance that you travel. You can still go backwards, is what I'm saying. Okay? What does it mean if I extend this graph out? We're almost done here. If I extend this graph out so it overlaps my axes, what does that point mean? Put it in words for me. What is that? You got a speed. You're going slower and slower and slower and slower. What happens right there? It stops. What happens here then? It starts moving again in the other direction. So that would be like doing this. Okay, you slow down, you stop, and you start going the other direction. What does that one mean up there? This is right at the beginning. This is at time of 0. That's telling me at time of 0 I was going. This tells you, like when we first start looking at the situation, it basically tells us our starting velocity, or starting speed. How fast you go when it's starting. Okay, your initial speed. Okay? Initial speed. So I'm just trying to remind you of what you can pull off of these graphs if you need to. Well, at this point for today, that's it.